So this is relative velocity, chapters 3.1 to 3.3. So we got to go back to motion is relative, and if we were to look at the example that we gave a few weeks back about if you're sitting on a bus and the bus is driving down the highway northward at 55 miles per hour, what is your velocity relative to the seat or the person next to you? And based on that example and many mentions of that example, you would know that you're not moving relative to the seat next to you. Okay? The bus is moving, but you're sitting in the bus. You're not moving relative to the bus, so you're not moving. So this example here, if you're inner tubing down the river, just like this baby, very happy looking baby is, are you moving relative to the water? If you had answered yes, you are moving relative to the water, you would be incorrect. And if you were said no, then yes, you are correct, because as you're just sitting and lounging on the inner tube, the river is carrying the inner tube downstream, but from the perspective of the water, you are moving right alongside the water, so you are not moving relative to the water. Much like the example for the bus example. Now, how about if you are moving relative to the shore? Like in the bus example, if you are sitting on the bus driving northward at 55 miles per hour, somebody standing on the side of the road watching you, you are moving 55 miles per hour relative to the person standing on the sidewalk. So, person on the inner tube, are you moving relative to the shore? If you had answered yes, you are correct. If you answered no, you are incorrect. Now, if you're sailing a boat and you want to move directly across to the other side, but there is a water current moving you downstream, how will you get to the other side? So think about it. What would you need to do to get directly to the other side? Now, if you were to want to get to point B, right, point B, and you're sailing your boat towards point B, and you're not considering the fact that there is a water current pushing you downstream, you'll end up getting this direction. Now, the red line on the bottom corner here shows you your resultant, because as your boat is sailing towards point B, the river current is going to push you downstream, so then the ending result of a person standing on the shoreline over here will see your boat going this way, not getting to where you want to go. So what will you do? Think about it. What will you do to get to point B? So to break this motion down, your boat is moving relative to the water by sailing directly across the river. Relative to the water. So in the water, that's what you're doing, just going from point A towards point B. However, there is a water current pushing you downstream, and anything in the water downstream. So as a result of that, which is a resultant, your boat is going to move downstream towards point C. And this motion is relative to somebody standing on the shoreline watching the boat going downstream. Okay, so back to the question. What will you do in order to get to point B? So this is what you do. If you had any sort of intuition about this, it will probably tell you that you need to kind of point your boat and sail upstream somewhat. So by pointing upstream somewhat, as the river current is pushing you downstream, it'll carry you directly across to point B. So if you're sailing upstream, diagonally, moving kind of upstream and forward at the same time, the river current is going to push you downstream, so that the end result will show that you're moving directly across from point A to point B. Okay? So now your boat is moving relative to the water by angling slightly upstream, and your river is carrying you downstream, pushing anything downstream, and the result is you moving up. So you can see that there are basically three vectors here, and that the vectors here and the vectors from the previous example, the resultant is not always going to be the hypotenuse. In this case, it's not. It's one of the sides. Okay. Another thing I want you to look at is that the components of the resultant, this component and this component, the boat relative to the water, the river relative to the shore, these two components make up this resultant. The boat is going to have, as a result, be moving straight towards B. Okay, so pay attention to the wording relative to the water, relative to the shore, stuff like that, and where the resultant is. Look at the head to tail rule. See the head to tail rule apparent right over here, And so then the resultant will always be connected from the point of origin to the point and ending position. Okay, so that's what you will be able to determine. So then now that brings us to the point where the wording for these types of problems are pretty confusing. So in order to avoid confusion, it might be a good idea for you to pay attention to the wording, the terms like relative to the shore, relative to the water, relative to the ground, relative to the air, stuff like that. That gets really confusing. But try to draw them anyways on a piece of paper and arrange them in such a way that they'll connect to form a triangle. Generally speaking, they'll always form a triangle, whether it's a right triangle, obtuse, or an acute triangle. Make them form a triangle anyways, but try to follow the rule for head to tail rule, but more importantly, always try to identify what is the resultant. So it might be helpful for you to go back and listen to the last couple of examples over again, or maybe a few times, just to match the explanation to the picture or the animation. So that way you have a better understanding of how the wording goes and what the relationships are from the wording to the actual motion of the objects. So in a very general case, normally when I say an object is moving relative to the air or an object is moving relative to the water or something like that, that is usually not the resultant. But when I say when it's relative to the shore, relative to the ground, relative to a tower or something like that, something stationary, then it is a possibility that is the resultant vector. So keep that in mind. So that gives you a little hint. Okay, the wording can provide hints for you. So the math involved is just like the math we did for vector addition, Pythagorean theorem, SOHCAHTOA, all triangles. You know, it's law of cosine, law of sine. So you can kind of follow this along. And using these equations will enable you to solve for a magnitude and also the angle of the resultant. So that's a pretty helpful hint there. So here's an example. If you have an airplane flying 100 kilometers per hour, okay, relative to the air, and the wind is blowing to the west at 25 kilometers per hour, the ending resultant is 103.1 kilometers per hour if you were to look at the triangle that's produced and using Pythagorean theorem to solve for r. By doing so, you'll be able to see that this r value is just a hypotenuse, just like in math. Okay? So as a result of the airplane flying due south at 100 kilometers per hour, the wind, and this is relative to the air, okay, this is relative to the air, and the wind is blowing 25 kilometers per hour relative to the ground towards the west. As a result of this, your airplane will be flying at 103.1 kilometers per hour, represented by the blue line here. And it's blowing, and from the ground, it looks like this plane is moving kind of diagonally. Now, to take it a step further, to find the angle here, and this angle here, let's just call this angle 15 degrees, let's just say. Okay? Let's just say this is 15 degrees. So this airplane, from the perspective of the ground, or an observer on the ground, or relative to the ground, this airplane is now flying at 103.1 kilometers per hour at, let's just say, 15 degrees to the west of north. So this west of south, sorry. So there's a south axis, there's our relative axis. This is what we're going to compare our motion to, our direction to. And so over here, this angle here, that's just 15 degrees. So you see how this is to the west of the south, right? So if you have a practice problem here, and a motorboat velocity is 20 kilometers per hour relative to the shore. Okay? So relative to the shore should give you a hint as to whether it is a resultant or not. But always read further to verify. If the boat must travel straight to the nearest shore in a river whose current is 12 kilometers per hour, what upstream angle must the bow of the boat point at? Okay, so then now this is kind of confusing. Try to draw an example And so using the same direction as the boat example given previously, going north is from point A to point B, okay, and that's where you want to get to directly across. What upstream angle must the bow of the boat point at? So go ahead and practice that and see if you're able to get an answer. So go ahead and pause and see if you can solve it, and do your best. So here would be the example. So going north, this is one example where the river current is going towards the west instead of the east as the previous example. But the idea is still the same. You see how you're trying to get straight across? That is what you want your resultant to be. And that's the velocity of the boat relative to the shore. Okay? So you can see relative to the shore, that is an indication that it could be a resultant. Okay? And then you have the boat's velocity relative to the water. That's usually never the resultant. Okay? And so you have to angle it upstream somewhat. And the velocity of the water relative to the shore, again, you see relative to the shore. That when you see relative to the shore, relative to the ground, that could potentially be the resultant. But since we're not concerned about the river, we're not concerned about the water current, we're only concerned about the boat. So then looking at the boat, that will give you a better understanding as, okay, this is the resultant. So the resultant is always connecting from the point of origin to the ending position. So you can see that this angle here, okay, is the angle you want to sail your boat into. Okay, by sailing your boat into the river current, you'll end up going directly across the river. So to do this, use the Pythagorean theorem to solve for the unknown side, and use SOHCAHTOA to solve for the angle. All right, and this is it. No more. All right. I'll hopefully you have more preparation for this, and we'll talk about this more in class.